Okay. So yeah, welcome everyone. Thank you for braving the storm. Yay! Yeah. So this week or this month, we have a duel here talking about subjective and video quality assessment. So without further ado, thank you, Abdul.
So I'd like the session to be as interactive as possible. I have collected as many visuals as it makes sense without making it boring. This is a topic that I did my PhD in, so that's not a good thing, by the way. Because I could go really in detail and do that for the video, so I don't want to do that. I thought it's important to talk about, when we talk about objective quality assessment, it's important to talk about subjective quality assessment side, because that's what the target is always when you measure quality. So that's why the two halves of the topic. Feel free to interrupt me at any time if you have any questions. So the story starts, this is sort of one form of the story that I'll lay all on. So you would see, here's a delivery chain. This is the war room for us, for video people, because we may be working on a specific part of the delivery chain as it's laid out here. So what's laid out here is in reverse. So here you have the viewer side watching on a specific screen. Here you have content creation. So as you see, it's in reverse order. The reason why it's in reverse order is because viewer is the most important part of the delivery chain. Typically, we would see that, okay, we have the content, we need to get that content to the viewer, and how would we get that content to the viewer? I believe that it should be the other way around, because viewer should be the prime when it comes to setting up a delivery chain all the way. So let's track backwards. You're watching something, you click on a video, you're watching something you like or you do not like the experience on that specific device, and you track it back all the way. So there may be a set-top box that's helping you play the video. There may not be a set-top box, so the decoder may be in the set-top box. That means the TV could be done. Or decoder could be in the TV. That means the set-top box, there's no need for a set-top box. It's software-based. Then there's a content delivery network. We talked about that quite a bit. For ABR-based delivery, there may be some packaging that's happening. So you could adapt based on network and playback conditions. Then you have some transcoding. So you could actually do the adaptive bitrate delivery. This is an ABR delivery chain that I'm looking at. For content, typically it's not one stage, so you have somebody contributing the content, so there's some contribution encoding that may be happening here that is typically high bitrate, and then there's the content creation process. So here's the camera may be capturing that. So you may have impairments or problems at different stages of the delivery chain, and we'll look at that in detail. One thing I would say here is the way video delivery chains are set up, every stage is meant to do the job just for the next stage. Typically, this stage is not set up unless it's a file. This is not set up to be watched here because you could not deliver that directly at scale. This is set up just to do its job until this point. This is set up until this point, this point, this point. So every stage is just serving the next stage. And the problem is broken down into multiple stages. The whole idea is to get the content to the viewer as faithfully as possible. So this is just sort of setting up the stage, and we'll talk about what can go wrong at different stages. Next. Any questions? Okay. So I'll flip it to here. Before I do that, I'll just flip the slide. Okay, so let's watch something next. So, it's a short clip, and I may pause at different stages of the clip. So you're watching the video as a viewer, and you may have some impairment here. This impairment typically called banding. And banding can happen because of your display device, because of display, it could be because of content, it because of compression, and then it obviously does not deliver the target viewer experience. Now you have another stage here. Here, obviously, because of compression, it's easier to guess. It's low bitrate, or the bitrate is low for the content that you want to deliver. And then you have a third one, which you will see in a bit, which is because of transmission. So here, you have some loss in packets that may be causing that problem in video, and all of that can happen when you look at that delivery chain. So all of that is part and parcel of the delivery chain. It can happen anywhere in the delivery chain. So different parts of the delivery chain are adding different impairments. And the goal at the end is to understand what the viewer is experiencing, and also to extrapolate from there onwards throughout the delivery chain, where anybody is experiencing what. The advantage of doing that is if you know the experience, let's say the experience here is 100, and the experience here is 50, you could, if you have a way of tracking experience, so you go from 100 to 90 to 80 to 70 to 50, on a specific display device, you could actually go back and optimize a specific part and set that up to deliver a specific experience. So that's the advantage of doing, one of the advantages of doing objective quality assessment. Any questions? Okay, so what can go wrong and where? I have a quick list. So this is not as exciting, but this list is just to get out of the way the typical things that you do not want to have go wrong. I call this involuntarily, you may introduce impairment. And there are some impairments that we add voluntarily, which is because of lossy compression and so on and so forth. So I'll talk about that. So typically connection availabilities, something cut a wire for fun or otherwise, configurations are not correct, IP address is wrong, there's data loss versus data delay, missing streams or flows, data bounds and metadata checks are not valid, content checks, not the right content, you want to deliver HBO, you're delivering something else, and then there are some protocols and syntax specific requirements that are not correct. So HLS, XML checks are not, they do not pass, anything like that. So these are some problems that if everything is perfectly set up, you should not see. But these can happen at any time. These are the things that we may voluntarily get. So we say, okay, 4K, 60 frames per second, that's fine. We can deliver 1080. Let's just downsample it to 1080. And that has an impact on, that can potentially have an impact on viewer experience. So you voluntarily reducing the quality. You do the frame rate, so 60 frames per second, downsample it to 30 to 24. Dynamic range comes in as high dynamic range content, you convert it into standard dynamic range. And you're on purpose reducing the quality. Display devices, watching it on a bigger screen versus smaller screen would change the viewer experience. Viewer type. So video people are specific type of people. So if you are working on denoising and somebody gives you video that has noise, you may be more critical to that video that has noise versus somebody who works in compression and you see some compression artifacts, you may not like those specifically. So viewer type is important. I believe, and we here also believe that there are 3 types of viewers that are commonly out there. One is naive viewer. So anybody who just wants to, sorry, who just wants to enjoy content. You're watching content, you're sitting on a sofa, you have beer in your hand, pizza maybe, and you want to watch the content, you want to enjoy that. The focus is not on quality, the focus is on the content. You would not want to worry about quality unless you are asked or you are jolted that now there's a problem. The second type of viewer is an expert viewer, what I would like to call it. So this is a person who is focused on quality for a living. So GoldenEye, you may have heard the name GoldenEye. So GoldenEye would come and say, I would tell you if encoder A performs better than encoder B. I would tell you if 5 megabits per second delivers the same quality as 3 megabits per second. So these are the people who would come and who would evaluate quality for you. Still, the goal is to represent the viewer, but they are measuring quality on viewers' behalf. The third type of viewer is a content creator. For a content creator, that's their baby. they actually do not want anything to be modified. So if I added film grain, I don't want you to improve compression performance by removing film grain and saying that, okay, who cares about film grain? Film grain is important because I created film grain on purpose. And they believe that everybody should watch content with their eyes because they define quality. They created the piece of art that they spend years and hundreds of millions of dollars on, and it should be, quality should be measured using their eyes. So as far as they are concerned, it doesn't matter if it's person's face, it doesn't matter if it's in the background, it doesn't matter if it's in the shirt, as long as there is impairment, that's bad. So the focus is on impairment than on content. You have viewing conditions, you turn off the light, you increase the brightness of the display, viewing impairments, viewing conditions would change impairments. Playback behavior, rebuffering, switching, the size of the player, all of that impacts. And then there's video processing. So that's an interesting topic. We can talk about that for about an hour. So this guy in here may claim that you give me 1080, I'll make it 4K like it's real 4K. It's going to be no different. Maybe it's better than the actual 4K that somebody created. Or we could create an 8K picture like it's the real 8K. So the video processing is meant to, and there's a film mode, there's the gaming mode, there's all sorts of modes. I'm not saying they're bad. I'm just saying that you do video processing that impacts quality. And that is also something we're doing voluntarily when we process content. A common example is encoders would implement video processing approaches for pre-processing. That would include denoising, that would include changing resolution, that may include sharpening and a lot of other things. The goal is to improve quality before encoding, so you could either make encoding easier or just remove impairment. Okay, what tools are out there to do that? So there are just a few examples. FFmpeg, GStreamer is another one. There are some encoding options that are open source, X265, X264. And if you scroll through this page, you would find hundreds of options, if not thousands of options. And all of this would have, hopefully, a material impact on quality. Otherwise, if those tools do not have a material impact on quality, then they are on the wrong page. So that means when you have an impact on quality, you're not dealing with something one or two or three different things. You're dealing with thousands of variables at the end of the day. And when you look at content, content lives in multi-million dimensional space. Every single pixel that you change can change the content how it looks. So mathematically, it lives in a multi-million dimensional space. So if you have a multi-million dimensional space that is interacting with, humans are not perceiving content pixel by pixel, which is why it's a multi-million dimensional space. So you have an interaction between a multi-million dimensional space, and on top of that, you have transformations that are out there. There are thousands of them. That means you're dealing with so many permutations and combinations. If you want to really solve image and video quality assessment, you need to have a model that can actually watch like a human and then provide that score. Doesn't matter what the transformation is, doesn't matter what the content is. So what do databases do? Databases try and study a subset of content that they believe, or the databases or creators believe, represent all type of content and all common types of impairments. This is one of the databases that has a lot of impairments. Typically, you do not find databases with these many impairments. So what do you find here? You have noise, all different types of noises. You have denoising algorithms, because denoising would add additional impairments. You have compression. This is an image quality assessment database, by the way, so no video impairments. You have JPEG, you have JPEG 2000, then you have shifts, mean, contrast, color, some other type of noise, and now you are getting into the situation where impairments overlay with one another. What if you have noise and you have compression on top of that? What would happen with that? So there are many different types of impairments here. So if I go to the database, it has 25 images, not very high resolution images, but 25 images. So these are the images that represent all image space. You tell me if these are enough. But these are the 25 images. So at the end, after watching these 25 images, you are drawing conclusions for all different types of impairment for all different content types. Now, if we look at impairments and quickly visualize those impairments, you would see an impairment type with impairment level increasing. So yes, some type of noise. So in this case, this is level 1 of the impairment type 1 of image 1. So that's what this title represents. So image 1, impairment type 1. So there are 25 images. There are 24 different types of impairments. And there are 5 different levels. That results in 2,400 test images. That means a subject may have to watch all 2,400 images and give a score. And I'll talk about what that score means. But so you have these different types of impairments. Some are more, some are impairing at that level more, that content, some are impairing less. So this is saturation, change. This is blur, compression, JPEG compression, there was JPEG 2000 compression because of ringing artifact. This is blockiness, so this is JPEG. Another type of compression. This is the block shift one that I talked about previously. So they're all different types of. The question is very simple. When you look at the image, what's your experience? And the question to the image quality assessment algorithm is also very simple. If I give you the pixels, what's the score that the person is going to provide? Okay. So the folder has all of these different images with different impairments. Okay. So that's what impairments look like from subjective quality assessment. Now you have some interesting examples. So over there you saw, okay, noise. Noise is bad. You build an algorithm, you say noise is bad. You deploy the algorithm, you see this. And you say that this is the worst picture on the planet based on that algorithm. But this is obviously not the worst picture on the planet. What about some other images? So if you have an image like this, would your model work on an abstract image? Would your model work on an image that was shot on a film versus digital? When you do quality assessment, is this better or is that better? Maybe if we do a poll, some people may say this is better. Other people may say that is better. What should the algorithm say which one is better? Okay, so overall, the advantages of subjective quality assessment: direct feedback from consumers of video content. The disadvantages are time-taking, expensive. You have to pay that. You're not going to do. You can make $10 online by clicking on images and getting a score. That's called crowdsourcing. So those ads that you see may be real. You can make money on them. And then it's not scalable. So that's the advantage. What are the things that you need to think about when you set up a subjective assessment database? These are just a few of them. You need to have a clear objective, what the goal is. Otherwise, you would get different types of responses. And people would not agree with one another, and that would be garbage at the end, the data that you would collect. You need to look at viewer's background and differentiate if you want to. You need to select content that's diverse. How many sequences? That's a good question. If you tell me, if you answer 25 of my questions, I'll tell you what sequences are good enough. Sequences are good enough. Impairment types and range. Obviously, you could have hundreds of different types of impairments, and you have 10 different levels, you have 50 different levels. What is right for the subjective test? What should be the viewing conditions? You have environments where you have chin rests, and you would fix your distance, and you put your face in the chin rest, and you're not allowed to move. And the lighting conditions would be fixed as well at the same time, and you have to watch it under those conditions. There are other subjective studies that nobody cares. You can go up to the TV, you can go far, you can do whatever, you can move away on the side. Um, should you do source versus output for encoding quality assessment? Should you do independently? What order should they appear in? Scoring methodology, what should be the range? What's the definition of that range? Should people provide score as they're watching video at all times, or should people watch the whole video and give a score at the end? What approach works for what type of test? How should you post-process scores? Are all the scores valid? Can some scores be invalid? How do you determine if those scores are invalid? And then number of subjects. Are 30 enough? Are 20 enough? Are 10 enough? Are 200 enough? 2 million enough? What's the right number? And what should be the duration of a session? Because after 25 seconds, 25 minutes, I've also seen people saying, oh, okay, I'm done. I'm just going to write whatever. So just let's be over with. Maybe half of you are thinking about this presentation right now in the same way, but I sympathize with that. But I've seen people do the same thing from subjective testing perspective. So that's a very quick overview of subjective quality assessment. Happy to answer any questions.
What's the right way?
So typically you would have somebody who would conduct the test. You come in. So we are, SIMWAVE is working on a subjective test with American Society for Cinematographers. Those guys are the guys who create content for a living. These are colorists, you know. So depending on what the goal of the subjective testing is, it would be different. But researchers typically do this. They would have a paper. They would write a prompt on the paper. Somebody would come in. They would read out of that paper. This is the goal of the subjective study. They would do some training. This is an example of good. This is an example of fair. This is an example of bad. So you know what you're dealing with. And you need to get your study approved by Department of Ethics. So you get them to sign that. Make sure that you're not taking advantage of them. That's an important part. Okay, so that's, and then typically you would want to do naive viewers. So when we did at the university, we would invite students. It's easy. You send out an email to all the graduate students. In half an hour, you have 200 people who want to participate because they will get $10 for that study. So you have lots of subjects because of that. So that's how you select. There are papers that study how people watch it in Europe, how people watch it in Nordics, part of the Europe, how people watch it. Are women more critical of quality? Are men more critical of quality? So if you want to study that, then you have to pick subjects accordingly, but typically you have a good mix of that. Video content selection. Typically out there, if you look at subject-rated databases, they are typically 5 to 10 of them. They're typically 6, 8, 10, 12 sequences, not more than that, not less than that. Your paper will not get accepted if it's too few. Impairment types and ranges. Typically, you have only one type of impairment per subjective study. So you would only study H.264 with a bitrate range or QP value of 22, 27, 32, 37, and then you would see how that would perform, unless you want to compare. So if viewing conditions vary quite a bit. Some reviewers are very picky. You have to have fixed distance, otherwise the mean opinion scores are not really valid. But typically you would have some range. You would not, typically people would not allow subjects to really go up close to a TV and watch that. Number of stimuli, they're both types, and there are advantages and disadvantages. So if you want to compute MOS versus DMOS, so MOS is something where you would do one image or video at a time, and you would not know which one is source, which one is output. You would give a score, and that would be your mean opinion score. And then if you want to compute differential MOS, then you would subtract the test score from the source, and that would give you the differential MOS at the end. So some studies would give you differential MOS, other studies would give you a MOS. But now you have paired comparison is a new approach. So you would, because there are so many permutation and combination, you would put two images together, and then you would randomly select those. And these, all you do is this one better, or is this one better? And the disadvantage there is that you could have 3 images where a subject may end up saying that this one is better than that, this one is better than that, and this one is better than that, and you don't know what to do. And that could be a challenge. So what we did at the university, and we try to do when it comes to images, we ask people to score and to rank at the same time, and we provide all the options if you're comparing the university algorithms. That's of course difficult with video. The scoring methodology and range, we have tried 0 to 100. 0 to 100, there's some noise. So typically, if you're watching video and you're an IB, would you say, okay, 76, no, maybe 77, no, I think 76. The people usually don't think that hard. So 100-point scale is typically over-complete, typically speaking. 0 to 10 works fine. 0 to 5 works better for certain applications, but you need to define those ranges for them. And you need to educate them on that. That's why the definition. Continuous versus discrete is interesting. So if you want to do continuous, you need to have equipment. It's not easy to do continuous without equipment. You need to have some equipment where you could have a dial and you would move the dial as you're watching the video. Now, different people have different response time. Some people, as the quality changes, some people will just quickly respond to that, other people will not. So with continuous study, you need to make sure you have alignment between subjects, otherwise you would not be able to get a consistent score. So post-processing, there's DMOS, MOS, depending on what sort of study, both are fine. Z-score is the length of the session length is recommended to not be more than 40 minutes. That's typically 30 to 40 minutes. You don't want it to be longer than that. If you want it to be longer than that, then you need to have a break. And then Z-scores are used to align scores from the same subject across different sessions. One day you're happy. Says, okay, great, I like this video, this is awesome, great job, 9. The next day, the same video says, I'm not happy, the weather is not good, why am I here? You give a 6. So you need to make sure that the alignment is there for the same subject, and you could do across subjects as well. And typically, number of subjects, if it's a good study, the number of subjects are about 30, 25 to 30. Somebody wants to do a great job, you may go to 50, but typically 15, 20. If you look at the industry where people select encoders, 2 people, 1 person says that guy is the expert, and that guy would make a $10 million decision by just comparing this and this for different. So I've seen it all. So those are typically the ones that we see.
I'm curious to know kind of the sort of studies that you were involved in where you kind of got to the end and were in the analysis phase where like, oh, we really didn't do this part right, or the content breadth was not good, or and sort of like what area, if you have had that, sort of what areas typically things have fallen down in. And I'm asking because I have.
Yeah, no, absolutely. So every time if you do a full-blown study, that's what you figure out, always. So what you would see is, for some content, people would only be in this 80 to 100 range. For other content, people are only in 20 to 70 range. And now you see, okay, I have to deal with this because it's not covering the full range as an example. So and you need to, of course, randomize the order. If you don't randomize the order, then you see some patterns, and those patterns don't make sense because those have noise. So what we typically do is we do a small scale study first and see if that small scale study is pointing out some problems and fix those, and then do a large scale study. Because there's always something that you ignore or you figure out afterwards based on this. And one way to test that is you compute the mean opinion score based on that small study. And then you leave out one subject. And then find the mean opinion score, and then find the correlation of that subject with the mean opinion score. So this is interesting that we usually use. So we have 5 subjects, and people usually think this is a test. So at the end they say, okay, how did I do? No, it's not a test. You're supposed to tell us what you think. So, but the way you find how typical you are, you would leave me, and for the rest of the 4 of us, we would do a mean opinion score. And then you would find correlation of my scores with the mean opinion score. And that will tell you how typical you are. So, but then what you would do is you would take turns. For me, for the second, third, fourth, fifth person, and then you take an average of that correlation of every single subject. And that may give you an upper bound of what correlation can you expect when it comes to objective quality assessment. Because even subjects may not correlate with one another to that level. And that may tell you if you really did a good job here. Okay, it's only half done. This is the second half of the presentation, objective quality assessment. And maybe this is more interesting, hopefully. So advantages, scalable, inexpensive, relatively speaking. Disadvantages, as I mentioned, lots of permutations and combinations. It's difficult to build something that's generic. So difficult science. The question is very simple. What's your experience? And you have pixels. What would you do? Would you compute wavelet transform? Would you compute discrete cosine transform? Would you try and think how impairment behaves? Would you try and think how content behaves? Where would you start? And it's so that's why you may end up computing lots of stuff. Let's just compute lots of stuff. So that's is the approach that say VMAF tries to take that approach and says, okay, let's compute everything. Let's compute a lot of metrics, and now we can fuse them together and see which one will tell the truth at the end of this, which one is closer to what the reality is. So at the end, you end up becoming too slow. And then, of course, accuracy is a challenge. Then to make things more complex, there are multiple types of objective quality assessment approaches. You can have no reference approach. You just give me the test sequence and give it to the algorithm and get a score. That's no reference. Second one is reduced reference. So you may not know what the source is, but you may know something about the source. And you may have the ability to compute that something about the source. So simple thing would be luminance, contrast, so on and so forth, but people don't really measure quality based on luminance contrast. So you want to do something more sophisticated than that. Something that would represent natural scene statistics, statistics of natural images. So when there's deviation from those statistics, you could measure the quality level from that. This may be possible because you may have a repository of video somewhere on the server side, you compute some features, and then you use those features somewhere you cannot have access to that, and to the whole set of videos, but just the features, and you compare features to quality. Then you have reference base, of course. In video encoders, that's what you do. You compute full reference quality assessment. That's the most common. That's the easiest thing to do from quality assessment perspective, because you have the source and the output fully available right there for you to do that. And then degraded reference is what we started working on. So let's say the source into an encoder is not pristine. So can we say the job of the encoder is to faithfully reproduce that not so good source, or is the job of the encoder is to create as good quality output as possible? If the job of the encoder is just to create a copy of the source, then you may fall short when the source is not good. But if you really want to do the best job, then you want to create an output that looks as good as possible. So that's degraded reference. And some popular algorithms, as you know, PSNR, structure similarity, multi-scale structure similarity, VQM. VIF is not so well known, but VMAF uses VMAF uses VIF as one of the metrics. It performs quite well. Then VMAF, as you know, and we provide C++ as an extension of structure similarity. Okay, so how to select an objective quality assessment algorithm? Before you design a subjective quality assessment, what's the success criteria? You want it to be highly accurate. The accuracy is correlation with subjective quality. There are 5 different ways or 6 different ways you measure that accuracy. Typically in papers, you find linear correlation, that's linearity. Then you find mean absolute error. So after you do a nonlinear mapping, you can find an absolute error between subjective and objective score. Then you can compute root mean squared error, that's just a different statistic. You can compute 2 types of rank order correlation. So you say, I don't care what the error is, as long as subjective test says this is the best score, this is the second best image, this is the third best image, and objective also says the same thing, that's fine. So there are two types of that. Rank order correlation coefficients, and the last one typically people use an outlier. And I'll have some scatter plots for visualization of that. Rank order correlation is the one that's most commonly used and that's most challenging. So that's typically saying if the subjective scores say this is the best and this is the second best, does the objective score say the same thing? That's very commonly used. Needs to be linear scale. PSNR as an example. What does 45 dB mean? Does 40 dB mean half the quality as 45 dB? Does it mean 1/3? Does it mean anything? Is the delta between 40 and 35 dB the same as the delta between 40 and 45 dB? Obviously, the answer is no. These are rhetorical questions, but it's good to know because you may work on an encoding optimization algorithm, and you may be extremely proud of yourself if you improve the PSNR value by 0.5 dB. And you tell your mom and you said, I improved the performance by 0.5 dB, and you may not know what that means. Nobody will know what that means. And you may say that's a big deal because I improved by 0.5 dB. So it's not easy to understand if it's not a linear scale. And you cannot really use that for constant quality encoding. Because if you look at it from a viewer perspective, you want to do constant quality encoding, quality from a viewer perspective. So you cannot do that if you don't, if 35 dB for animation means different quality than 35 dB for sports. And that is going to happen. 35 dB across different content types does not mean the same quality at all. So you're targeting for 35. That may not be the right objective. You're targeting for 40 may not be the right objective because you may hit a lot higher quality for some content type, a lot lower quality for other content type. So consistent performance, that's what that means, and normalization across content, viewing conditions, device, and viewer type. So you could encode for a bigger screen, you could encode for a smaller screen, you could encode for something else, you could encode for 2 times the height, you could encode for 4 times the height. If somebody tells you this is where the viewer is sitting, this is what the screen is, can you optimize for that? Resolution, frame rate, and dynamic range. So if you say I have 4K coming, I have 8K actually, I have 8K coming in, and I have 8K Dolby Vision source coming in. And you say that right off the bat, I'm going to convert that to 1080 and SDR. What's the impact on quality? Is the impact on quality the same when you take a picture here? It's the same when you take the picture here, because these are two different types of pictures. This requires a lot higher dynamic range for you to see the details in the background than you take the picture here. And the impact is very different. Is it general purpose? It only works for compression, only works for luminance shift, it only works for a specific impairment. Can this be computed across multiple points in delivery chain? That's how we started. And can I use this for encoder optimization or any other optimization playback? So these are the things that you want to consider. Here is the performance is scaled up. This is the performance of PSNR. So this is the source. All of these images have exactly the same quality when it comes to PSNR. There's no difference in quality when it comes to PSNR between all of these images. Because mean squared error is 144 here, 144 here. Mean squared error, so PSNR is the inverse of mean squared error and then a log. This is actually the best image because the mean squared error is the smallest among the 5 of them. And then it's 144, 144. And structure similarity, the open source algorithm, obviously says these two are better than the other 3. May not be exactly the right rank the way you would want to do it, but it differentiates between them in the correct way. And this is a reference-based approach where you're actually using that as a source. So this is a mean shift, this is a contrast shift. Because of upsampling, it's not supposed to be broken, it's just a low resolution image we're displaying on a large TV. This is JPEG compression, blur, and salt, pepper, noise.